Okay, so plan today, guys. We're going to go through an algebraic proof for the triangle inequality. So if you can open up your notebooks to that page. Now, this isn't a strict exercise in our textbook, but it is something that pops up in complex numbers, and it does pop up in vectors, and they ask it all the time in the exam. They love the triangle inequality for some reason. So we're going to spend a whole lesson exploring it. There's 3 proofs for it. I'm going to go through the first one, which is just an algebraic proof. I think that makes the most sense. And I've written it down on the page for you, so you don't need to write it down. It's on the left-hand side of the page. So I'll just explain it, and then you can have a look at the cosine proof and the vector proof as well. And then we'll go through a few of the questions together, and then we'll just continue with vector proofs. Okay, so we're sort of summarising the triangle inequality as part of the vector proofs component, and a question about it will probably pop up in the test on vectors. Okay, so let's just talk about what it means first. Let's understand it geometrically. So if I have vectors A and vector B, the triangle inequality says that the modulus of vector A plus the modulus of vector B is larger than or equal to the modulus of vector A plus B. Okay, so we can see if I add the modulus of this and the modulus of this, all right, if I were to get my ruler out and measure it, and measure that one and add them together, it's going to be longer than this one. Okay, it's going to be greater. The only circumstance when they are equal is when A and B are parallel, when they're going in the same direction. So if I have vector A and vector B, then the modulus of vector A plus the modulus of vector B would equal the modulus of vector A plus B. Okay, so that's the circumstance in which they're equal, and this is the circumstance in which the modulus is greater. So it's an inequality expression that holds, that considers the direction. So let's talk about a proof for it. I'm just going to start with vectors A and B. I'm going to start with this expression. We have the modulus of vector A plus the modulus of vector B squared. I'm going to perform a perfect square expansion. This is what it expands to. And one of the properties we have of modulus is that the modulus of A squared is equal to A squared. That's true by definition. Okay, so just as an example, if I have minus 2, the modulus of minus 2, and then I square that, well, the modulus of minus 2 would be positive 2, and positive 2 squared would be 4. And similarly, if I just have minus 2 squared, well, that evaluates to positive 4. Okay, so this is a property of modulus, that the modulus of A squared is equal to A squared. So all I've done from this step to this step is replace the modulus of A squared with A squared, and the modulus of B squared with B squared. Notice how I've got they're equal. This is equal to this because the modulus of A squared is equal to A squared. Okay, then I'm going to introduce an inequality. All right. Now the substitution we're going to perform is this second property, is that the modulus of A is greater than or equal to A. Now, if A is 2, the modulus of 2 is 2. So in this circumstance, the modulus of A is equal to A. All right, so that's the equal circumstance. If A is minus 2, all right, then the modulus of minus 2 is positive 2, in which case the modulus of A is larger than A. All right, and so here we have a definition of modulus. The modulus of A is either equal to A when it's positive or greater than A when A is negative. Okay? So if that's okay, then all I'm doing is I'm saying this expression here includes the modulus. So that means this expression here has to be larger than or equal to this one here, dependent on the values of A and B. Okay? So it'll be equal if both A and B are positive, and will be greater than if A or B is negative. All right. So because we've swapped, because of this definition here, the modulus of A is greater than or equal to A, and I've replaced both of those terms. I've replaced A and I've replaced B. Modulus of B with B. All right, and then we're looking at that and going, okay, well that's just a perfect square, so we can factorize it to that. And one of the properties of modulus is that A squared is equal to the modulus of A squared. So I'm taking A plus B squared is equal to the modulus of A plus B squared. Okay, so I'm maintaining equality on the right side, and we've got that inequality stated here, so that this side is larger than or equal to this side. Now we know the left-hand side, we started with this. All right, so what do we have on the left-hand side? The modulus of a plus b squared is larger than or equal to the modulus of a plus b squared. And then we're just square rooting both sides. We're left with the triangle inequality. Okay, that's the algebraic proof for it. You're not really needing to know the proof, just that it's a true statement and we're going to apply it. So let's get straight into the questions that you guys have on the page there. The questions, we'll go through these I think together. So I'll rub them out and we'll get started on the first one. So, get my notes up here. We have question set 1, 2, 3. All right, verify that the modulus of Z1 plus Z2, so I stated it like this, didn't I? Modulus A plus modulus of B is larger than or equal to the modulus of A plus B. And obviously, it can be flipped. If we flip the inequality, we can have the modulus of A plus B is less than or equal to the modulus of A plus modulus of B. Okay, they are the same statement. So, verify that this is true given Z1 and Z2 here. So these are complex numbers. We'll start with both of them. We've got Z1 is 3 plus 4i and Z2 is 6i. All right, so on the left-hand side, we're going to have the modulus of Z1 plus Z2. So how are we going to answer this? Let's start it like this. Let's just say we've got Z1 plus Z2. We need to show that Z1 plus Z2 is less than the modulus of Z1 plus the modulus of Z2. Okay, prove this. So let's go. For the left-hand side is going to equal the modulus of Z1 plus Z2. And then we're just going to drop them in there. We've got 3 plus 4i plus 6i. That's the modulus of 3 plus 10i. Which is the square root of 3 squared plus 10 squared, the square root of 109. All right, we'll go to the right-hand side. On the right-hand side, we have the square root of 3 plus 4i. Let's write it out slowly first. We have the modulus of 3 plus 4i plus the modulus of 6i, which is the square root of 3 squared plus 4 squared plus the square root of 6 squared. This is going to be the square root of 25. This is the square root of 36. We have 5 plus 6, we have 11. So the right-hand side is 11, and the left-hand side is the square root of 109. Now, I can see this is true. Therefore, true in this circumstance. I can see this is true, and I'll explain why. 10 squared is going to be 100. 11 squared is 121. So that means the square root of 121 is 11. So the square root of 109 has to be somewhere between 10 and 11. All right, which is less than 11. Okay, so it's true in this circumstance. All right, so that's A. I can let you guys do B, but all you're doing is plugging it in to verify that they're either true, that it's either less than or equal to. Now, you'll be able to see the circumstance in which it's equal because Z1 and Z2 will be parallel. They'll be scalar multiples of one another. Okay, let's move on to the second one, where this is where we're really pointing out how SACE likes to ask it in exams and so forth. So we have OPQR is a parallelogram on the Argand plane. All right, so fix that a little bit there. OPQR, and we have Z1, and Z2. We have this vector here, PR, and this vector here, OQ. Okay, it's a parallelogram. Z1 and Z2 are complex numbers. Find in terms of Z1 and Z2, OQ, the vector from O to Q. All right, now, O, because it's a parallelogram, OP is parallel to RQ and equal in magnitude. That means RQ is equal to the complex number Z1. And so then the vector from O to Q is going to be Z2 plus Z1. All right, and then the next one, find PR, the vector from P to R, from P to R. So it's going to be minus Z1 plus Z2. Or Z2 take Z1. Very good. Okay, explain from the triangle inequality why the modulus of Z1 plus Z2 is less than Z1 plus Z2. All right, so what we're going to consider here, Z1 plus Z2, that's triangle OQR. So let's abstract to that and speak specifically about triangle OQR. So I've got O, I've got R, I've got Q. Now I love to abstract these kind of shapes because I think it really draws out the region we're interested in. And what we have from the triangle inequality. So let's make a statement from the triangle inequality. From triangle inequality, what is evidently true here, we would have OR plus RQ, okay? Side OR plus side RQ is going to be greater than or equal to OQ. Now I should stress modulus of those. And so what that means is Z2 plus Z1, the modulus of Z2 plus the modulus of Z1 is greater than or equal to the modulus of Z2 plus Z1. And how do they want us to state it? They've flipped it around the other way. The modulus of Z1 plus Z2 is less than or equal to. Okay, so in the last step, all I'm doing is rotating the inequality 180 degrees, putting that on that side, flips the inequality. Okay, so from triangle inequality, we've considered that triangle and we've demonstrated that this is true. Okay, explain from the triangle OPR. They tell us the triangle we're talking about, triangle OPR, so we'll abstract it again. That's going to be this one, OPR. Why is it true that the modulus of Z2 takes Z1 is larger than or equal to the modulus of Z2 takes Z1? All right, so here, let's come up with a triangle inequality statement. So what we can do, I mean, we can state it in any way, but the modulus of OP plus the modulus of PR, they're the vectors we've got vector PR, so let's do that. The modulus of vector OP, okay, from here to here, plus the modulus of vector PR from here to here is larger than or equal to the vector from O to R. Now we've found all of those, okay. Vector OP corresponds, oh sorry, I've written those around badly, haven't I? We've got O, I should make it look the same as what we've got here. This is P and this is R. Okay, vector OP plus vector PR is larger than or equal to vector OR. It doesn't matter the order we're going to write it in because we can fix it after anyway. Okay, so vector OP is Z1. Vector PR is Z2 take Z1. And vector OR is vector Z2. Okay, so based off of our description here, we have the modulus of Z1 plus the modulus of Z2 take Z1 is larger than or equal to the modulus of Z2. Now it's very close to what we're asked to say, all we need to do is subtract the modulus of z1 from both sides, and we'll end up over here. Okay, so just to communicate it properly, all right, all you need to state right at the start is from the triangle inequality, okay, this is the definition of the triangle inequality, that the sum of two sides is always larger than or equal to the third side. It doesn't matter what two sides you pick, because as you saw down here, we can just adjust it by subtracting from both sides to get what it wants us to show. Good. Now, question 3, use the PMI, principle of mathematical induction, to show this is true. This is going to be a good opportunity for us to recap PMI. Okay, so we will go through this problem together. So let's clear the board. I'm going to write small because I've only got one board, and we'll fit it all on here. Now, don't expect this to fit in your notes book. You can write it down in your book if you want. But it's a good opportunity just for us to recap what are the skills associated with PMI. All right, use PMI to show that this is true. Okay, so the P of N is, this is what we start with. We start with the claim that we're testing, plus all the way up to ZK. Is less than or equal to the modulus of Z1 plus the modulus of Z2 plus all the way up to the modulus of ZK for K is a positive integer. Okay, so that's our proposition. So from PMI, I always like to remember state, okay, which is state the proposition, test the proposition, assume P of K, prove the proposition, and then explain. All right, so we've stated our proposition, we're on to test. So let's test for n equals 1. The left-hand side is just going to be the modulus of Z1. The right-hand side is going to be the modulus of Z2. Therefore, true for n is 1. All right, when n is 1, we have equality. All right, we don't have greater than or equal to, we have equality. So let's test for n is 2 to see if we can get the inequality. Now, on the left-hand side, we would have the modulus of Z1 plus Z2. And on the right-hand side, we would have the modulus of Z1 plus the modulus of Z2. Okay, if we're just considering the first two iterations of the proposition. Now, we've actually proved this is true. We did the algebraic proof at the start of the lesson. Okay, so we won't redo that, but we can just say true using algebraic proof. Okay, so in this circumstance, in the first case, we've demonstrated equality is true. In the second case, we've demonstrated not only the equality, but the inequality is true as well. True using algebraic process that we demonstrated earlier. That's where you would make that argument. Okay, so we've stated, we've tested. Okay, now let's make the assumption. Assume P of K. Now, I'm really sorry. This should be in terms of n, shouldn't it? Because we have an nth proposition and K, and now we're assuming for K. Assume P of K, and we're just basically restating what we've got here. Z1 plus Z2 plus all the way up to Z of K is less than or equal to all the way up to Z of K, or K is an integer. Assume P of K equals that is true. No, we'll put the true. It is true for K is an integer. Save myself a line. All right, assume P of K is true for an integer. All right, so we've stated, we've tested, we've stated our assumption onto the proving. Okay, so we can write prove, or we can write consider P of K plus 1. Okay, So we'll consider the left-hand side. P of k plus 1 is going to be this expression, z1 plus z2 plus all the way up to zk plus z of k plus 1. Okay, so we just write the whole thing to z of k, and then we have the zk plus 1 case. Now, what I'm going to do next is simplify this expression, all right? I'm going to describe all of this as the sum of z of k, okay? Of the z of k terms, all right? Because that's what we're doing, we're adding up all of the z of k terms. So that what that gives us then is we have the modulus of the sum of zk terms plus the zk plus 1th term. Alright, but if I add up all of these numbers together, that's going to give me one number. So I have one number plus whatever the zk plus 1 term is. Now we know from the second circumstance that when we only have two terms inside, that is, sorry, I pointed that the wrong way, it is less than or equal to the sum of zk plus the modulus of zk plus 1. Okay, that's proven in our second step here. All right, that the modulus of z plus 1, z1 plus z2 is less than or equal to the modulus of z1 plus z2. So all we're doing is using that there. And this is where we plug our assumption in, okay? Our assumption was, now this is the sum of zk, so maybe I'll write that out a little bit first, just because we just did substitution. All right, so that, this was just a definition that I used, okay? The sum of zk is that. All right, and here's where we use our assumption, is that the sum of all the way up to zk equals z1 plus z2 plus zk. Okay, so that's our assumption, that's where we're plugging it in, plus the modulus of z of k plus 1. Okay, so if our assumption's true, we've demonstrated that the left-hand side equals the right-hand side. P of k plus 1 is true. Then we say, because P of 1 is true and P of 2 is true, to demonstrate the inequality, because P of 1 comma 2 is true and P of k plus 1 is true whenever P of k is true, therefore P of n is true via the principle of mathematical induction. So, stated test assumed, proved, and then the last step is the explain. Does that make sense? We remember doing that a bit? PMI. Okay, so pretty sneaky doing the sum of z of k. We know it works for that one. Here's our substitution from there to there. Okay, that's our assumption. We're assuming that's the case. That's where our substitution occurs. Okay, so look, if you want to practice the triangle inequality, you could answer those questions again, or you could answer B that we haven't done. And they will pop up a little bit in some of the vector proofs. For now, let's dedicate the lesson to, I think, continuing with the vector proofs, whichever question set you're up to. Of course, I recommend doing all of them, but yeah, that's our plan for today.